Welcome to another of my presentations. My name is Guy, and I'll be your guide through the intricate world of the microbiome. Our topic is ulcerative colitis. As usual, I'll be highlighting the key microbial players and how they are a large part of the root cause. With ulcerative colitis, like with so many conditions, there is a genetic component which sheds light on the disease but does not explain the rates of occurrence and growth. Again, lifestyle factors are absolutely crucial. It's this combination of lifetime exposures with possible genes, which may lead some people to a diagnosis of, say, depression, while others may get rheumatoid arthritis, and another ulcerative colitis. And an unlucky bunch may have all three. In fact, depending on the reference, some 20 to 50% of UC patients suffer from depression or anxiety. And these numbers are even higher in active disease. And on top of this, many are undiagnosed. Again, it's all connected. The similar themes of dysbiosis and inflammation driving these things we call diagnoses. So for those of you who suffer from UC, or those practitioners who treat UC, let's get started and expand your knowledge base. I'm not going to spend time on drug options for UC, and very little time on surgical possibilities and genes, which themselves only explain about 16% of UC cases. I have other plans for this video. Suffice it to say that UC can have terrible outcomes. And as for cancer risks, one can only imagine that there are increased risks for colorectal cancer in UC patients. And there are, which become astronomical for patients diagnosed at childhood from 0 to 19 years old. But there are other cancer risks as well, like liver cancer. As for surgery, approximately 20 to 30% will require surgery during the course of their disease. The most notable is shown here, called the IPAA. During this surgery, the patient's large intestine and rectum are removed, and the small intestine is connected to the anus. The last few inches of the small intestine are used to create an internal pouch, which serves the function of a rectum. By preserving the anus and creating a new storage place for stool, patients are able to maintain control, quote unquote, over their bowel habits. I'm not sure how much control that is, since after the IPAA procedure is complete, patients will usually have 4 to 6 bowel movements per day. Plus, the cells of the small intestine aren't meant to serve as a rectum. This all just sounds awful. Of course, your other choice is to walk around with a bag attached to you, which you have to empty out. Why not just address the root cause? That sounds so much better. But we live in a highly profitable world of drugs and surgery and not common sense. So then what is the root cause? Well, back in the 1940s and 60s, a number of researchers thought the cause was from dairy products. Not the lactose, which is everyone's first thought. It's the proteins. They are much more serious than the lactose. One study claimed that ulcerative colitis was often due to food allergy at least 66% of the time. Another removed dairy foods from the diets of 6 UC patients, and they all improved. And when they reintroduced dairy, in every instance it was followed by a frank attack of ulcerative colitis. You can see here in figure 1, also from the 60s, that these researchers found 7 times higher immune reactivity to the dairy proteins casein and lactoglobulin as compared to healthy controls. I even have my own story to share. Many years ago, I was helping a woman with UC. I put her on my regimen, which included the avoidance of dairy products. After a week or two, people were commenting on how much healthier she looked. She was putting on weight, and of course, she reported to me great progress. However, being new at things, she made a mistake. She had a salad in a restaurant which had a dairy-based dressing on it. After having been stable for weeks, she dramatically regressed overnight with bloody diarrhea for the next 3 days. And dairy products are not a problem unique to UC. They are a problem for IBS, Crohn's, and as you can see here, for type 1 diabetes. That's type 1, the autoimmune version. No other protein is introduced earlier in life than that of dairy. So if you're not breastfeeding or not doing it exclusively, then odds are you're using a dairy-based product. You should know that there are numerous studies going back many years associating dairy consumption with type 1 diabetes. I'm not going to get into the detail about the various protein and peptide culprits found in cow's milk, but I will say that although there is a human genetic component to type 1 diabetes, the lifestyle component plays a larger role across the board. If you look at figure 3, the countries with the highest consumption of dairy products also have the highest rates of type 1 diabetes. In a separate Finnish study not shown here, Finland, by the way, is the country consuming the most dairy products per capita, children who consume the most milk had over 5 times the risk of developing type 1 diabetes versus the lowest consumers. But for these children and for our UC subjects previously, dairy is not the root cause. It's an immunological situation after the fact. This autoimmune response has to do with dysbiosis, inflammation, intestinal permeability, and genes. Let's start with dysbiosis. This is the microbial fingerprint for UC. After years of reading all available human fecal microbiome original research papers comparing UC subjects to healthy controls, I've compiled the data here for the keystone taxa within this profile. As usual, green is good and orange is bad. Let's hit some taxa from left to right. First, we see Bifidobacterium. But wait, it's mostly orange. Is the genus Bifidobacterium a health promoter? Well, normally yes, but in the case of UC, in particular active and more severe UC, the data is not pretty. We'll cover this more later, and I'll explain why I do not recommend Bifidobacterium probiotics in active UC. And frankly, they aren't needed anyhow. The next two, we see classical opportunistic pathogens from just about every one of my presentations, Enterococcus and Escherichia. That's where E. coli comes from. It's not shocking to see that their data is 100% negative. Next, we see Lactobacillus, that other so-called probiotic, once again with the signature of an opportunistic pathogen for like the millionth time. Watch my presentation entitled Lactobacillus Probiotics, a Dumb Idea and Those Who Are Dysbiotic to learn more. Or just watch every one of my presentations because it comes up all the time. Next, we see R. navis, which is also a part of the microbial fingerprint for Crohn's, the sister disease to ulcerative colitis and IBD. Next, we see another classical opportunistic pathogen, Streptococcus, not surprisingly with almost 100% negative data points. And lastly, we see another opportunistic pathogen which comes up frequently in my presentations. Now, since I can only highlight so much material per video, I'd like to touch on something a little different each time, and this time we'll hit on Veillonella. Here are my data points for the genus Veillonella across all diseases for which I've done a meta-analysis to date. As you can see from the mostly orange bars, it has a typical opportunistic pathogen profile. Not as ugly as, say, E. coli or Enterococcus, but still an opportunistic pathogen nonetheless. We see particularly large spikes for Crohn's, ulcerative colitis, IBS, liver health, and C. diff. Now, in the past, I've said that most bad bacteria come from the phylum Proteobacteria, which is true from a certain perspective. When you consider the number of overall pathogens in the gut in relation to the number of species within each phylum, then yes. And the poster child for opportunistic pathogens is E. coli, which comes from Proteobacteria, which has that highly immunostimulatory LPS that I'm always talking about. However, there are others from other phyla, like Veillonella here, which is within the phylum Firmicutes, which is where most of the good guys come from. So why is it bad when this phylum has so many good actors? Like its cousin opportunistic pathogen R. navis, which is highly troublesome in both Crohn's and UC, they are both members of the phylum Firmicutes. While R. navis produces an inflammatory polysaccharide, see my Crohn's presentation, the species from Veillonella are actually gram-negative, which is odd for Firmicutes, and produce endotoxic LPS. There's that LPS again. Of course, some LPS, like the LPS from E. coli, is much more pro-inflammatory than others, like say from Bacteroides species. But the LPS from Veillonella seems to be comparable with that of E. coli. That's a bad thing. The other thing that Veillonella is known for is that it's a big lactate fermenter, which is why you probably almost always see it elevated along with Lactobacillus, a huge lactate producer. This goes back to my video on pH and lactate accumulation. We have to control the environment. If not, the bad actors will work together to control it for us. If we look at some original research analyzing the microbiota, we see here that the superhero of the gut, F. prausnitzii, when its abundance was high, was associated with remission, whereas when its abundance was low, there was a higher UC relapse rate. Of course, one of my goals is to feed F. prausnitzii, along with the many other keystone health promoters significantly reduced in UC, which we saw in my microbial fingerprint chart from earlier. But not all prebiotics are suited to all conditions. Here we see very high rates of cellular invasion by Fusobacterium varium, along with very high levels of inflammatory markers. Although this species and genus are not a part of the microbial fingerprint for UC, it may help explain the significant higher rates for colorectal cancer in UC, as species from this genus, Fusobacterium, are the #1 microbial suspects in colorectal cancer. See that presentation. And here we have two quotes which back up a couple important aspects from the microbial fingerprint. One, that Bifidobacterium was significantly increased in the biopsy specimens of active UC patients compared to those in the healthy controls. And two, compared to healthy controls, Faecalibacterium prausnitzii was sharply decreased in both the fecal and biopsy specimens of the active UC patients. And I had to include this study for a couple reasons. In this UC study, we see an almost who's who of good versus bad in the microbiome for UC versus healthy controls. And this utter dysbiosis has numerous consequences, one of which is on the bile acid composition, which I bring up frequently. Bile acids, which are hormones, play many roles in our intestinal and extraintestinal health. As you can see in figures C and D, the two key secondary bile acids are markedly reduced in the UC subjects as compared to healthy controls. That's a bad thing. And in J and K, the two primary bile acids are significantly higher in UC versus healthy controls. Also a bad thing. This dysbiosis-driven perturbation in bile acid metabolism sets the stage for a C. diff infection, for which having IBD is a key risk factor. See my presentation on C. diff. And here, in this very dense figure 4, we see a clear division between bile acid metabolism in various taxa. First, we see that there are many different bile acids here, but we'll only focus on the two primaries here and the two key secondaries here. In the top right is our key for correlation, red positive, blue negative. We can see a clear division here. And we see here that are well-established opportunistic pathogens like Veillonella, Enterococcus, Klebsiella, Streptococcus, and once again the so-called probiotic Lactobacillus are all associated with the primary fecal bile acids, whereas our well-established health promoters here, like Roseburia, F. prausnitzii, Luminococcus, Fusicatinibacter, Gimager, Carpococcus, Allostipes, and Odoribacter, are all associated with these secondary bile acids in the feces. Now, before I dive into the mucus barrier and various facets of the immune system, let's just consider the GI tract. Whether it was a year ago, 1,000 years ago, or 100,000 years ago, we've been drinking from streams and eating sources of food which have some degree of pathogenic load. The GI tract is the most probable route for pathogenic exposure in our body, which is why some 70% or more of our immune system is in our gut. The defenses need to be in place. The GI tract is tasked with a tough job to break down and absorb the valuable things we ingest, while at the same time sort out the things we don't want. But we make its job even tougher by throwing an endless barrage of obstacles at it, and for the purpose of this video, resulting in what we call ulcerative colitis. Ulcerative as in ulcers, colitis as in colon. The colon is the part of the GI tract with the largest amount of bacteria, and it is here that the mucus layer is very complex. It's the first line of defense, and not just against ingested bad actors, but normal bacteria present within our collective microbiome, opportunistic pathogens who are waiting for the right set of circumstances to become opportunistic. And we're all too willing, it seems, to help them in their endeavors. Mucus may sound like a simple concept, but at the core of mucus is Muc2, one of the most complex proteins synthesized in the body. An increased demand as a result of aggressive bacteria, for example, might push this complex synthesis, leading to release of suboptimally assembled Muc2 and generation of a lower quality intermucous layer. Because when bad bacteria come into contact with our cells, a robust immune response is waiting. This is well established. Mucus is made from what are called goblet cells. There are several types of goblet cells and various types of mucin. But we're going to simplify things and talk about the double layer of mucus protecting the cells that line the colon. Goblet cells do a lot more than make, store, and secrete mucus. They also recognize danger and secrete many other crucial proteins. And mucus is just not mucus. Within it are a host of antimicrobials and other components. The mucus in the colon has two layers, one firmer, thicker, and attached inner layer, meant to be sterile, and a thinner outer layer. The protein backbones, which form the structure of mucus, are covered in several different sugars for protection, which are locked behind bonds we can't access. But some bacteria can, and some of these bacteria possess more of these enzymes than others. But first, they have to get through the caps as seen here. And once cleaved, this outer layer is open to a community. The community can be a health-promoting one or a nefarious one. It depends on the environment, which you're largely in charge of. In Figure 1, you can see those caps in turquoise and mahogany. Now, there are bad actors like R. davis, which is a problem in both Crohn's and ulcerative colitis, who can break these initial bonds. And there are generally good actors like Mucinophylla and Bifidobacterium bifidum, who can break them as well, but appear to do so less aggressively. When the good guys are in charge, the outer mucus layer is a health-promoting one. Classic good guys like F. parasitii, Roseburia, and E. rectale will take up residence here, be cross-fed by other bacteria, and effectively crowd out the bad guys. When this happens, butyrate is produced. Butyrate is incredibly beneficial for the colon. It is the primary fuel source for the enterocytes, supports mucus production, enhances intestinal barrier integrity, suppresses inflammation, and much more. When the bad guys are in charge, then butyrate is not available. Bad bacteria adhere to and invade cells, enterocytes turn to glycolysis, resulting in increased lactate and oxygen levels, all causing a series of worsening events. When this happens, there is great compromise in every aspect of mucus. It's every building block, the health and abundance of goblet cells, everything. So the key is to keep the health promoters in charge of this environment. For UC, it's clear that Akkermansia mucinophylla is a health promoter. Its abundance is consistently significantly reduced in UC. But the strange thing is Bifidobacterium. Bifidobacterium has good data for when UC is mild or in remission. But when it's active, the data shows that it's consistently, significantly higher in abundance in UC. Why is this? Well, we do know that a number of species from Bifidobacterium possess a host of enzymes able to degrade the sugars that coat and protect the protein core. In fact, these sugars are almost identical to the sugars in breast milk, the human milk oligosaccharides. And we know that Bifidobacterium is the #1 beneficiary of HMOs. Just look at the table I built. Those amazing health-promoting fuels during breastfeeding are also present in mucus. So it's natural that Bifidobacterium would use them for fuel. And we know that the mucus layer is severely compromised in UC. So the bonds are more exposed. On one hand, this can explain why there's more Bifidobacterium in the microbiome during active UC. But on the other hand, A. mucinophylla is also a mucin-loving bacterium, which is consistently reduced in UC. Wouldn't the same logic apply? I can't offer up a good explanation at this time, but erring on the side of caution, I do not recommend Bifidobacterium in active ulcerative colitis. But that's not a problem because we want butyrate producers. Here we have a species from the phylum Actinobacteria. That's where Bifidobacterium comes from. At the bottom are the enzymes which degrade the bond within mucus. Here are a number of species from Bifidobacterium. The lighter color indicates a strong presence of the enzymatic ability, while black, a lack of presence of the genes to make the enzyme. As we can see, Bifidobacterium bifidum has almost all the genes necessary to degrade mucin, including breaking those first protective caps. But Bifidoadolescentis has very little. And if you've seen my video on resistant starch, you know that Bifidoadolescentis is one of the 2 primary degraders of resistant starch. Here we see species from the phylum Bacteroides. We see a lot of species from the genus Bacteroides, with a lot of enzymatic ability. This is not necessarily a bad thing. And here we see species from Proteobacteria, that generally bad-acting phylum. We curiously see very little enzymatic ability. It seems they may have to wait for some cross-feeding from other opportunistic pathogens who operate under the same environmental conditions as they do. Perhaps from species like Enterococcus, which contain a broader array of enzymatic potential to degrade mucus, or from R. navis and R. torquis. And here, just to give you an idea of the complexity of things, each of those enzymes is actually a family of enzymes, each targeting a specific bond to access a given fuel. Bad bacteria also have a number of methods of adhering to the mucin and penetrating it. When the balance is shifted in their favor for fuel, oxygen, enterocyte metabolism, and pH, it's a bit of a spiral down. This whole process being set off by antibiotics, a bad diet, PPIs, impossible genes, stress, or an enteric infection, or possibly COVID, which have been shown to dramatically alter the microbiome, similar to a number of other infections. See that presentation for COVID. It is due to the disappearance of the oxygen-sensitive, pH-dependent, butyrate-producing health promoters that got us started down this ugly path. The inhibition of beneficial symbiotic bacterial colonization by opportunistic pathogens is mediated by degradation of those sugar bonds, to include that initial step of liberating fructose and sialic acid, which seem to promote disproportionately the growth of pathogens like E. coli. I'd like to quote one powerful statement from this paper, which says, "As a result, the structure of mucus layers is impaired, and host susceptibility to pathogens and even ulcerative colitis incidence increases. Therefore, UC was postulated to be an energy-deficient disease resulting from a failure to utilize butyrate." Bifidobacterium does not produce butyrate. And they didn't say it's due to deficiency in soil-based organisms, for all of you who keep asking me about that. And it's certainly not due to a deficit in lactobacillus. Lactobacillus contributes more lactate to this dysfunctional environment, and then Veillonella is happy to consume that lactate. And don't forget, Veillonella has pro-inflammatory LPS in its cellular membrane. Do you see how this is all a vicious circle? We can see it here in this in vitro study, looking not at fecal bacteria, but at the mucosal bacteria. They found that R. navis and R. torquis abundances were dramatically increased in both Crohn's and UC samples, while A. muciniphila was reduced many-fold. R. navis and R. torquis secrete enzymes capable of removing the terminal sugar caps to degrade mucin. Once the terminal sugars are removed to expose the oligosaccharides in the protein core, the mucin matrix becomes easily degradable by a host of other colonic bacteria. And the protein core is made up of amino acids like threonine, and which bacteria in general tend to like to ferment amino acids? The bad guys. And they really like threonine, which is especially rich in mucin. Like I said earlier, all aspects of mucus and goblet cells are compromised in the hyperinflammatory state, to include their numbers. In figure B, you can see how the actual number of goblet cells were significantly reduced in UC versus controls in this in vitro study. And in figure C, how the surface area covered with mucin was also significantly lower in UC versus control. One way to address the dysbiosis of UC is via FMT, fecal microbiota transfer, as shown in this study. You can see the study design to the left. Just to know, when we look at figure B, T0 is the time of the first infusion, T1 is the second, and T2 represents the third. In this study, the FMT group did not outperform the control group, but there is a lesson to be learned. For the responders to FMT, several genera had higher abundances which populated the UC microbiomes, such as F. prausnitzii and A. muciniphila, whereas in the UC non-responders, they had higher abundances of Peptostreptococcus, a bad guy, especially bad for colorectal cancer, Veillonella, which we highlighted earlier, and once again, Lactobacillus. Other than confirming my data points, the study illustrates that when using FMT, it's important to select the right donor for the right condition. And in this FMT-UC study, they achieved clinical response in 95% of the subjects at week 8. But you can see at month 18 and 24, the rates of remission are far lower than for the first 12 months. This highlights something I talk about frequently, that the new microbiome has to be cared for. Perhaps the new owner doesn't eat healthy or exercise or takes a medication that negatively affects the microbiome or has genes that can push the microbiome into a less than desirable direction. In order to sustain benefit, The new microbiome has to be fed the fuels it needs to keep the health-promoting bacteria in charge, to prolong the benefits as long as possible. FMT can be a bit extreme, if not hard to find. What I propose is the next best thing to FMT, driving significant change in your microbiome with properly blended and dosed prebiotics suited to the need of the UC dysbiotic microbiome, which is the microbial fingerprint slide from earlier. Not only have I done the complete meta-analysis for all microbiome studies for UC, but I've also done a complete meta-analysis for all of the key prebiotics. I know which taxa they tend to feed, taxa which truly play roles in your health. Let's address the root cause, which I hope I've made clear in this presentation. And in my other presentations, the same themes exist. Once you've watched enough of my videos and you begin to be educated on how the microbiome impacts your health, you're welcome to work with me and take charge of your healthcare. If you found this presentation informative, I have many more for free in my YouTube channel and also in the Microbiome University tab on my website, themicrobiomeexpert.com. There you can select from a wide variety of topics. And if you or a loved one are struggling with a disease/condition, I have condition-specific presentations as well, along with their microbiome protocols found within its respective tab on my website.